understand her example. I have to make up my own. Hi everybody, my name is Caroline Richardson. I want to welcome you back to Make the Grade. This is Thursday. This is our last day for going over math questions and EOC review questions and questions for this, not season I guess, but for this school year. So hopefully everyone's been successful and hopefully you've enjoyed being able to have someone to call into and get your questions answered. Today, just like any other day, when the number's going to pop across the screen, and if you have questions on your math homework or your teachers have given you some review questions for your EOC, or parents you're trying to help your child study, just give me a call, and if you get stuck on something, I will be more than happy to go over that with you, okay? Today what I'm going to do until I start getting some calls is I'm going to review some Algebra 1, some Geometry, and Algebra 2 EOC questions. And you can get a copy of these questions if you don't already have them at the Wake County website. Let me pop that up for you. If you go to www.wcpss.net and do a search for EOC review, or just do a search on Make the Grade, then you'll see where the questions will be. Also, here's the phone number, which is 217-2203. So if you have any questions today, just give me a call. And then finally, here's the website. Those of you who aren't taking your test till next week, if you have some questions, I'll check the website every day and get back to you. I'll get back to you via email, or if you leave me a phone number, I can call you. Otherwise, email at mathhelp@wcpss.net and email me any questions you have. And then I want to ask another favor. If you've had an opportunity to see the show or watch and there's something that we can do better to make this more successful for you next time, email to mathhelp and let me know how you liked it and let me know what we can do to make things better, okay? All right, and then finally, since it's on the piece of paper, I'll go ahead and tell you. If you go to http://EWTV for East Wake TV.org, you can see the show live on the web. So if you can't be near the TV, or you have to leave for a little while, you can go to the web or call somebody if they need to see the problem. And they archive the show, so if you don't have time to review with me right now, you can go back and see the show and see some of these problems that I'm reviewing, okay? All right, so we're ready? I'm ready. If you're ready, I'm ready, okay? Ready. Let's look at some Algebra 1. Now I'm going to try to emphasize today just using the calculator and how you can not just answer the question. I certainly want you to know the algebra that's involved. You're going to be going on Algebra 1. You're going to be going on to Geometry and Algebra 2, and this is not going away, okay? And even though I'm doing an Algebra 1 problem, Geometry and Algebra 2, I need you to pay attention because you might come across something on your test that's very similar, okay? All of the math that you've learned up until this point, you're expected to know. So all those formulas, anything you did, let's say, 3rd grade or 4th grade, you still have to know. You're like, oh, of course I know that. How many of your careless errors have been because of arithmetic? Well, when did you learn that, right? So we're going to take some time today to go over some strategies. I want to talk to you about actually taking the test and looking at your answers and how we can put some of these into the calculator. First strategy. You know how you have the test booklet and there's questions on the left and questions on the right, and you do question 1 and you go over to your answer sheet and you bubble, bubble, bubble. Then you do question 2 and you bubble, bubble, bubble. Did you know that it's a different part of your brain that's actually doing the math versus doing the bubble, bubble, bubble? Because bubbling is kind of like art. So sometimes if you could do just maybe a page, do those first 4 problems, do the math, and then go over and bubble, 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 you'll be in a much better groove. Have you ever been working on your homework and the first couple problems you're just dragging, and then all of a sudden you just start rolling with the homework? Well, you've got yourself into a mindset of doing the work. You can do the same thing with the test. You don't have, nobody's watching you and seeing you bubbling each problem. Take a second. You can write in the test booklet. You can circle problems. You can say, review this one again, or skip this one, come back. Just always be sure that when you're matching the problem you're doing and what you're bubbling. Do the 2 pages, then bubble. Let your brain take a rest, then go back and do some more. Okay? Sometimes you make less errors when you're bubbling and less errors when you're getting back into the math when you do that. Okay? All right, well, let's look at this first one. Denisha, oh, you can't see that at all, can you? Zoom in. Here we go. Denisha bought a car for $15,000 and its value depreciated linearly. That's a tough word for me. After 3 years, the value was $11,250. What is the amount of the yearly depreciation? All right, well, let's get an idea of what's going on. If we think about the car, the year she bought it, whatever year that was, let's just say year 0, the car was valued at, say, $15,000. Okay, so maybe this is the 15,000 mark. And then it said it depreciated, which means the value went down over time. So here's year 1, here's year 2, here's year 3. It went down linearly. I don't know why I'm having a hard time with that word, which basically means a line, right? So it's going down. So by the time it gets to year 3, it's right here at $11,250. And then it will continue down. Okay, now it's not realistic. I probably didn't draw this very well. It's not realistic. It might go below the line. It's very rare that you would sell your car and you would give somebody money to actually take the car off your hands. I guess that could happen. But it depreciates and goes down. So what we could do is let's go ahead and make a quick little XY chart to kind of represent what's going on here. And that would be at 0 years, meaning when you bought it, it's at 15,000. And at 3 years, it's 11,250. All right, so a couple representations. Meaning, how much did it go down when you went a year? How much did it go down a year? How much did it go down when you went a year? Well, what do we call that whole concept of when you y-axis? Right, we call that slope. That whole rise over run business, right? All right, so basically what this is asking for is what is the slope? So even though these numbers are a little bit big and obnoxious, you can still do the slope. So it would be the change in y over the change in x. And notice all of our answers are positive. So I wouldn't get too carried away. We know that it depreciated. So you can make sure that your answer is positive just by doing basically the large number over the small number. But don't worry if you actually put the wrong values in there and you get a negative, because the negative is representing depreciation at this point. So 11,250, there's your change in y, over the change in x, which would be 0 minus 3. See how my numbers are going to work out to be negative? So if I take it, that would be 3,750 over negative 3. And of course, we kind of want the negative because it's negative slope. Oops, just on my picture. So what does that work out to be? Well, what's 3,750 divided by 3? 3,750 divided by, and I'll divide by negative 3, gives me negative 1,250. And what did I say? The negative was helping us represent the slope, which was this depreciation. So again, depreciation would be negative, so really that would be C. All right, so don't worry if your signs are off a little bit. You need to look at the problem and see what it's asking you. Depreciation is a type of negative, just like debt is negative, that sort of thing. All right, so that's a good question. Let me go wide a little bit just so I can remember. I got a graphical representation so I could see what was going on. I took my values, made an XY chart so it made sense in terms of the data. I made an understanding that this meant rise over run, and then went ahead and solved for slope. All right, that's a good question because a lot of times you get points and they just come straight out and say, what is slope? And that was a great way of looking at it, to think that, all right, depreciation over a year, that was something over time, right? Money over time. All right, let's look at another one. More money. Problem 2, there we go. Problem 2, in 1994, the average price of a new domestic car, oh, it's all about cars. They must be thinking you guys are getting close to your permit and driving cars. Okay, let's see. In 1994, the average price of a new domestic car was $16,930. In 2002, the average price was $19,126. Based on a linear model, what is the predicted average price for 2008? You know, almost every time I see linear model, that's going to tell me that maybe I want to jump over to the calculator and do some sort of linear regression. Is that ringing a bell? Let's get my values straight. So if we try to create an XY chart, in 1994, the price of a new car was $16,930. In 2002, the price was $19,126. I don't know about you, but if all I was looking at was the XY chart and I said write an equation, you would look at this completely different than reading all these words and numbers. So it's worth your time, worth the extra time to take a second to look at the word problem and get your data organized. All right, so I want you to write an equation with these two, basically 2 points. Well, I'm not saying that you can't do this by hand, but let's go ahead and do this on the calculator. So some of the steps we need to do, we need to put our x's into L1 in the stat and put our y's into L2. So we're going to do stat and edit our list, right? I should put those in squares, I guess. And then after we do that, we're going to actually do the linear regression on it. And then I talked a little bit yesterday, and I want to talk a little bit now. We're going to create the linear regression, and then we want to go ahead and put it into the y equals in the y1 position. And that way we'll have our actual equation, because one of the questions is what is the predicted average price in 2008? So what we really want to do is create our XY chart and find out, well, what happens at 2008? I know you can do this all by hand, but I want to show you how we can do it by the calculator. And then just as a reminder, we're going to see how accurate that is, so we're going to talk a little bit about R on the calculator and the accuracy. All right, so what should we do? Well, first thing, I'm going to clear my calculator. Let's go to our stat and put these values in our list. So if I go to the calculator, there we go. If I go to stat on the calculator, edit, and oh, wait, you didn't see that. They're already in there. You can see I was practicing. Hold on. Let's quit. All right, well, first thing they're going to do is clear your memory. So I'm going to go ahead and clear the memory because I have to show you something else too, so this will help. All right, everything is cleared. Actually, I don't think I cleared it right. 7, all RAM, reset. There, now it's happening. Okay, so let's try that again. So we go to stat, we go to edit. Whew, there we go, nothing in our list. So 1994. Now what you can't see is that I am touching on the paper the numbers I'm typing in. That way I don't make a careless error. 1994 with 1994 is 16930 and 19126. All right, so there's our values in L1 and L2. It's basically our XY chart. So the next thing we want to do is we want to do the linear regression. So we hit 4 for linear regression. And if we hit enter now, sure enough, it gives us our A and our B, which represent, what does A represent? We'll see how it says y equals ax plus b. That represents our slope. And b represents the y-intercept. And these numbers aren't too obnoxious, so you could retype them. But if I hit the y equals button, see how there's nothing in the y1 position? So what I want to show you is how can we take what's on this screen and go ahead and have it put it automatically into the y1 position. All right, well, you know how in your calculator, let's see if I can get it up on the screen. Really should have brought that overhead. It's not in the bag. Look up here on the screen real quick. Remember how if you did something like 20, actually you can go to the calculator a second, 20 divided by 6, go to the calculator, hit enter, you get 3.333. And the other choice is you could say 20 divided by 6, and you could hit the math button and tell it to put it in fraction form. So you have the choice with the calculator on how you want your output to look. You also have a choice of where you want the output to go. So one of the choices, if we come back to the actual screen, here we go. One of the choices is right here is vars, which stands for your variables. See it? Vars. Hopefully it's focusing a little bit. It's trying. Anyway, under the vars is where it's going to basically allows you to set up variables. And the variable we want to set up is the variable that goes along with this y equals. All right? So what we want is in this first y equals position, we want to put the equation from our linear regression. All right, so let's show that really quick. And now you can go back to the calculator. All right, so we have all the information in the stat. So when you go to stat and you go to calc and you do the linear regression or quadratic regression or whatever it is you might be doing, at this point hit the vars button and it's going to say, okay, variables, the variables in the window, no, we want the y variables and we want the 1, the function, and it's asking you which one of those do you want it to put in. Remember when you hit the y equals, it gives you all kinds of equations. We want it to put it in the y1 position. It doesn't matter where you put it. So it's saying, just like you did with the fractions, it's saying, okay, do linear regression, put the answer in y1. You know, just like you would change it to a fraction. So you hit enter, and you didn't see anything happen, but look, if I go to y equals, it put the exact equation in there. Now, why is that so powerful? Well, the equation is in there, one that's going to help you in terms of, you know, not make any careless errors when you type it in. But if we go back to our problem, the problem was asking for, now that we have our equation, what is the predicted price for 2008? All right, so if we go to the calculator, fastest way is we can go to the table. And the table starts at 0, so we can go down until we get to 2008. Okay, 4 years later, we're going to make it, right? So what's a fast way? Well, think about it. If you were, you'd set the table and more company came, wouldn't your mom say, go reset the table? Well, there's a second function window allows you to what? Reset the table. So we want to start it at 2008. It'll jump us right to 2008 on the table. We go there. Sure enough, 2008. It says that our y value is 20,773. So if we come back to our answers, it said what will be the value at 2008? It was 2,700. I'm having a tough time with that number. 20,773, which is C. Now, I know it took me a while to talk through that one, but it certainly won't take you long to type that into the calculator. A lot less chances for careless errors. The last thing is this R. I want to remind you of this R button, and that is basically, now of course there was only 2 points. Given 2 points, what are the chances that it's going to actually create an equation through 2 points? Well, pretty good, I'd say, because for any 2 points there's a line. But let me just show you on the calculator. If you go to the catalog, go down to your D's, what you're looking for is for it to do some, here it is, diagnostics for us. You have to turn the diagnostic on every time the computer's reset. So diagnostic on, hit enter, and done will pop up, so now you know it's on. Now if you do the linear regression, linear regression, 4, enter. See that R that popped up, that R equals 1? Well, what is 1 in terms of percents? Well, that's 100%. So sure enough, if we come back to the paper, I had R equals 1, which represents 100%. What are the chances that the 2 points I gave you, or that the equation they came up with made that equation hit all the points? Well, 100%, because 2 points. Now, if I'd given you some more data, maybe it did its best, maybe it only hit 99%, so R will change. All right, so look for that when it's trying to ask you how valid was the equation that you came up with. Okay, so that's what you're looking for, that diagnostic on. All right? Now, when your calculator gets reset, the very first thing they're going to do is reset that calculator. You want to be sure that you take care of that. All right. Whew, that seemed like a long problem, didn't it? All right, let's look at problem 4. All right, this one is dealing with velocity, the whole idea, the whole idea that, you're throwing up an object and what comes up must come down, that sort of idea. Or if you were, swinging a bat, you're going to swing it, the ball's going to go up, and then eventually it's going to peak down. Well, have you ever had to, football, that's one where they throw the ball in the hang time, right? It gives the players enough time to get down the field. Sometimes you need to know, what is that hang time? How long before it hits the top, before it starts coming down? How much time have we got to get down the field? So this equation is one of those equations that you need to memorize. And you will use, this one is in the problem. They may give it to you, they may not, but it is something that you should know. All right, so let's look at this. An object is fired upward at an initial velocity, v0, or v sub 0, at 240 feet per second. The height, h at t, of the object is a function of time, t, in seconds, and is given by the formula h at t equals velocity times time minus 16t squared. This is a formula that should have come across your table a couple times. How long will it take the object to hit the ground after takeoff? Okay, so it's fired, the object is fired, and basically it's traveling, and the question is how long is it going to take before it hits the ground? Okay? Again, that might be a football, this is an object fired, it may be something out of a cannon, who knows? Excuse me. Well, they gave you v sub 0. They gave you where it started. So let's put that into the equation. So we have a function. Oops. Thank you. So we have the function h at t equals v sub 0 times time minus 16t squared. And they gave us v sub 0. So the question is we're trying to figure out the time. We're looking for t. So that would be 240. I'm not going to put the units in there. T minus 16t squared. All right, at this point, stop worrying about the words in the word problem and look at the actual algebra. What do you need to do? If I asked you to solve for t, what would you do? Well, you'd set this equal to 0, correct? And you would factor and solve for t. There's a couple different ways you can factor. The easiest way right now would be to Factor out the t, that leaves you with 240. Oh, I take that back. We can take out 16t, can't we? 16 goes into 240. Yes, it does. So we can take out 16t. 16 goes into 240 15 times. The t's minus. 16 goes into 16 one time, and we're left with a t. So what does that mean? Well, if 0 equals 16t, or 15 times 15 minus t, using one of your laws of algebra, any two numbers a and b multiply to give you 0, then either a equals 0 or b equals 0. So now what? We solve both cases. This one we divide both sides by 16, so t equals 0. This one we solve for both cases. We get negative t equals negative 15, so t equals 15. Well, if the object is in the air, it's not going to make sense that it would take 0 seconds, so that one doesn't even work. So here we go, 15 seconds. 15 seconds is how long it will take the object to hit the ground after takeoff. 0 doesn't even make sense. It wasn't even the air. It just crashed, I guess. There we go, B. Whew, good one, okay. Hopefully you can see that. All right. All right, well, let's look at another one. Let's look at this one, and then maybe we'll do some geometry. All right, number 5. Can you see that? Yeah. All right, given f of x equals negative 3x squared plus 5, what is the range of the function? Even if they hadn't used the word function, you know it's a function by this notation, okay? There's other ways for you to know it's a function, but they did give you the notation and they told you. So the next question is, what is the range? All right, well, let's talk a little bit. What is range and domain? Domain, see what domain ends with? Domain ends with the word in. So that's the way I remember it. Domain is the things or the values that go in. So a lot of times these are the x values. Now that's not always, but that's for what you're doing with, it'll be your x value. So it's the values that are allowed to go into the function. So when they're talking about domain, this one's talking about range, but I'll go ahead and talk about both. When they're talking about domain, are there any limits that can restrict you putting a number into an equation? All right, well, think about it. If I just had y equals 2x plus 4, and of all the values in the world, every value of x that exists out in the world, is there any value that will cause any type of problem with this equation? Well, no. I could put anything from 0.000000057 to 3,921. I could put any number in there, and it's really not going to matter. I'm going to come back with a valid answer for x. Or, sorry, for y. So what am I talking about? Well, maybe if you looked at one that does have restrictions, what if I gave you something like 2 divided by x? Are there any values that I can put into this equation for x, for the domain, values that go in, that will cause a problem with this equation? When I say cause a problem, I mean make it an equation that you can't solve. Well, sure, if we put 0 in for x, and I had something like 2 over 0, well, that's undefined, isn't it? That's not something you can do, at least at this point. Okay, so if that's not something you can do, then there's a restriction on the domain, meaning every number in the world can go in for x except 0. So fractions are something you need to pay attention to for domain. The other restriction comes with your radicals. What's one of your restrictions with radicals? Well, at this point in Algebra 1 and Algebra 2, you've learned a little bit more about it, but really, if you think about it, what types of numbers, if I gave you y equals the square root of x, what type of numbers can you not find the square root of? Well, you can't find the square root of a negative number. Now, Algebra 2, I know you're saying, no, we know what that is now. But really, you can't find the square root of a negative number. But can you find the square root of 0? Yes, the square root of 0 is 0. The square root of 2 is whatever the square root of 2 is, 1 point something, 1.1, it doesn't matter, but you can find that, okay? But can you find the square root of negative 3? No, because it's the negative. So one of the restrictions that is placed on the domain there is that the fact that you can't have negatives. So you need to watch for radicals. Now this was a square root. That rule changes slightly. If I gave you the cube root of negative 8, can you find that value? Yes, you can. So the cube root of negative 8 actually works out to be negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So that's legal. So what am I looking at? I'm looking at when there's an even root in the index. So square roots, fourth roots, sixth roots, those are the ones we're talking about. All right, so let's talk about range then. Well, range is the same concept except now we're talking about what are the y values. Of all the values I can put in for x, what type of values will I get back for y? Well, if we look at this very first example I gave you, y equals 2x plus 4, if I can put any value in for x, isn't it possible I will get any type of answer for y? And one of the ways you could do this is you could type this in the calculator, and you'll see that this line will extend all the way through. And that'll be one way that you'll see that, in this case, it would be all real numbers. What about this one for this y? Well, on the graph, there's actually going to be a hole on the graph when x equals 0. But otherwise, all the y's will be represented except for that very point. And actually, if we put this in the graph, you'd see that it would approach and approach and approach and approach, and you'll get a very interesting graph for it. And radicals, well, if you can only take the square root of positive numbers, or 0, or positive numbers, then won't the answers you only get back will be 0 and above? Okay, so there would be a restriction on the domain, I'm sorry, on the range, where it would just be all your positive real numbers and 0, okay? All right, so that's what you want to look for. So in our question over here, now that we get back to the actual question, now that I reminded you, is negative 3x squared, let me rewrite it bigger, negative 3 x squared plus 5. Are there any values that can, are there any values that cannot go into the function? Well, all the values that go into it, they're going to get squared, so we don't have to worry about negatives, or there's no fractions or radicals. So any type of number can go in. So what type of numbers are going to come back out? Okay, what are those range? Well, the lowest case that can go in here where it will affect it would be 0. So let's say I put 0 in. Then I'll come back with y equals 5. So if I put in 0, I get y equals 5. If I put in 1, I get negative 3 times positive 1. Hold on. Negative 3 times positive 1 squared is still 1, plus 5 would give us what? Positive 2. If I put in negative 1, I also get 2. All right? So those are going to start bouncing back and forth. So there's our vertex, right? 0, 5. So in terms of the y values, what type of y values are we going to get? All the y values in the world? Or will we ever get a y value that's greater than 5? Well, I don't think you're going to get any bigger than 5. So one of our choices is all real numbers less than or equal to 5, all integers less than or equal to 5, all non-negative real numbers, all non-negative real numbers. What are those? All non-negative real numbers. Well, that would include 3. Are we ever going to be able to get that? We'll see. Or are we ever going to be, I'm sorry, not 3, like 10? Are we ever going to get 10 or getting a number bigger than 5? All non-negative integers, that's implying that you can't get a fraction. But if I put in a number like 1/2, I could potentially get back a fraction, right? Sure, because negative 3 times a half would be negative 3/2 plus 5. Sure, we get a fraction there. All right, so the integer answers aren't working for us because we can get numbers that are fractions. So which one's working for us? All non-negative real numbers or just the real numbers less than or equal to 5? Well, hopefully you've been able to see just from this it's going to be the numbers less than or equal to 5. Now, real quickly on the calculator, if I type the same value in, clear out my old one, if I type in this equation, negative 3 x squared plus 5, and I graph it, woo! Do you see there on your x-axis? Well, you can't see me pointing to it, but you can see on the y-axis, it goes up, 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 hits the 5, and then comes down, 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 down. So is there going to be anything higher on the y-axis? No. All right. So there's several ways for you to approach that problem, and that's the answer A. Now, I know I took a second to remind you what domain and range were, but you will see this. Algebra 1, you're going to see it. Algebra 2, you're going to see it. Geometry, I don't think you'll see it, but it's a fair question they could ask you because it's something you did in Algebra 1. All right. All right, so there's some Algebra 1. Okay? Let's look at a little bit of geometry. All right, first thing we're going to talk about is some of the matrices in geometry. You all, that's one of the new, I just lost my train of thought. That's one of the new goals that was put into the geometry curriculum over the last couple years, and is one of the new things that is being tested this year, okay? So one of the things you have to know is how to manipulate the matrices, how to add them, how to subtract them. But really what you're trying to do is if you had a shape, say you had a triangle with 3 coordinates, what would happen if I translated it? What would happen if I reflected it? And using matrices to do those transformations. So let's look at this first one. And there's nothing on your screen. There we go. Let me zoom out. This is tricky. That'll be one of the things I'll put on my list of things to do is I need to make some of these wider, or longer, but not wider. Okay. Triangle GHJ with vertex matrix -3, 4, 3, 6, 3, -2 is dilated by a factor of 1/3. Considering the image G prime, H prime, J prime, what are the coordinates of the vertex that lie in the second quadrant? Well, there's a couple different ways we can do this. First thing, especially if you're not sure what's going on, is I would go ahead and plot these points. Ooh, look at that pretty pink. So let's go ahead and plot these. Now, what are they representing? If we look at the vertex, let me zoom in a little bit. If we look at the vertex, it said it was triangle GHJ with matrix. Well, this is representing your X, and this is representing your Y of point G, point H, and point J. So that's how it's set up in a matrix, where you have your X's and those coordinates and the Y's and those coordinates. So if we go ahead and plot those, let me go back out for you. Isn't that cool? All right, so G is at the point -2, 4. So -2, 1, 2, 3, 4. H is at the point 3, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. And J is at the point 3, -2. 1, 2, 3, 1, 2, J. And I'm going to use my little cheaty ruler, which I know you made. And if you have no idea what I'm talking about, I simply, when they give you that graph paper, I want you to cut a piece in half, and I want you to fold one of it to be a ruler. And use that graph paper, creates a ruler, creates a calibrated straight edge that you can use to measure and approximate values. So, not that this one is asked for it, but see here, if it asks me what is the length of HJ, of course I know you can do the distance formula, but you could also say it's 1, 2, 3, 4, 5, 6, 7, 8. It's about 8 units long. Coordinate system's not going to lie. So that's a fast way for you to get your answers and check your answers if you can't remember your distance formula. All right, so there's our triangle. So the question is it's dilated by a factor of 1/3. Now, what is dilation? Dilation is an enlargement or a reduction. So here's the scale factor. So the scale factor, if the scale factor is greater than 1, then that's an enlargement. If the scale factor is less than 1, it's a reduction. So because this is 1/3, we are reducing the picture. So it's going to be a triangle smaller. What would happen if the scale factor was equal to 1? Okay, well, that would just be the same picture, like a stamp. Be congruent, and that's possible. All right. All right, so considering the image G prime, H prime, what are the coordinates of the vertex that lies in the second quadrant? So if we dilate this by 1/3, if you take this picture and you shrink it by 1/3, can you picture that? Well, let's go ahead and just do the mathematics involved with it. That would mean that we're going to take this matrix. We're going to take this matrix, -2, 4, 3, 6, 3, -2. And if we're going to dilate, that means we're going to take each one of those and shrink it by 1/3. So we're going to do scalar multiplication and multiply it by 1/3. So what do you do? That basically you distribute that 1/3 to each one of those coordinates. So if I say 1/3 times -2, our new G prime, and there's our X coordinate and our Y coordinate. Our new G prime would be 1/3 times -2 would be -2/3. 1/3 times 4 would be 4/3. Just leave them as fractions. That's much easier to deal with, trust me. 1/3 times 3 is 1. 1/3 times 6 is 2. 1/3 times 3 is 1. 1/3 times -2 is -2/3. Now, and that would be our H prime and our J prime. Now you can go ahead and plot those, but the question is what lies in the second quadrant? So if it lies in the second quadrant, what is the signs? Well, first quadrant is positive, positive. Second quadrant is negative, positive. Third quadrant is negative, negative. Fourth quadrant is positive, negative. Whoops. So we need a coordinate that the X is negative and the Y is positive. X is negative, Y is positive. Look at that. There's only one. So it would be the G. Now, if we look at our answers, I didn't even take a second to look at that. if we look at our answers, we also wanted second quadrant. So negative, positive, A could have been a choice. B, negative, positive, that was a choice. C, that's positive, negative. That one was gone before we even got started. And D is positive, positive. That one's gone before we even got started. So you can eliminate sometimes your answers. And I bet if we had looked even just a little bit harder at these numbers, we would have been able to see the negative 2/3 very quickly. All right, so regardless of what type of answers they give you, you need to look at what's going on, look at the keywords that they're giving, things like second quadrant. Remember that dilation is nothing more than scalar multiplication, and be very, very careful of your signs. This problem was all about the signs, wasn't it? Okay, so the answer is B. Yay! All right, good one. And if you had plotted that, wouldn't it have worked out to be a tinier little triangle because it would have shrunk. Right? Oh, well, you couldn't see that, but I just drew a small little triangle. All right, let's try another one. You mean you want to do more transformations? Okay, I will. Calm down. All right, let's do the second one. Which describes the transformation shown? Oops, there we go. All right, which describes the transformation shown? All right, well, we have GHI, and down here we have G prime, H prime, I prime. So looking at that, can you see that the G, the H, and the I are in the same relative position? They haven't, it's almost, well, I'm trying not to say the word without saying it, but still didn't bring my overhead. But if I take this, and you can't see, but I can. Now remember, on the test, you're allowed to have an overhead. I'm sorry, colored acetate. So talk to your teacher about it before the day of the test. You can't ask the day of the test. So there's G, there's H, and there's I. So if I take this, hold on, we're being flexible, we're being flexible. So if we take that shape, how does it match up with this other one? Did we flip it over? No, because the G is still in the same position. So really what did? We slid. Right, slid? We slid it down. Is slid a word? That doesn't sound right when I say it out loud. So we made a slide. We transformed or translated it. So that's what happened with this one. So when we look at our answers, a reflection over the x-axis. Well, if we took this and reflected it over the x-axis, that would put our G on the bottom. All right, here's our G right now. It's upside down. Here's our H. See, that's nice when you have the overhead. So my permanent marker is pretty much doing the same thing because it's seeping through. So it isn't a reflection over the x-axis. That would put us down here. A reflection over the y-axis, that would put us over here. The next one says, my new x prime, y prime, I took the x coordinate and subtracted 8, and I kept the same y coordinate. All right, well, let's look at these coordinates and see what happened. Our original G coordinate was 1, 6. Oh, and you know what? Let's do this in a matrix just so we emphasize that point, okay? So our original x and y for G was 1, 6. Our original H was 5, 5. And our original I was 1, 2. And our new values, I'm getting squished here, but you can see it. Our new values for G prime right here were 1, negative 2. H prime was 5, negative 3. And our I prime was 1, negative 6. So if we just compared these numbers, what's changing? What is changing in the x's? 1, 5, 1, 1, 5, 1. So the x coordinate didn't change at all. What's changing in the y's? We went from 6 to negative 2. How does 6 become negative 2? Well, if we add or subtract 8 from 6, we'll get negative 2. Does that work for all of them? 5 minus 8 gives us negative 3. Yep. 2 minus 8 gives us negative 6. So right there showed you what your possible rule is. And see the two choices here? Our two choices were saying, okay, manipulate the x, subtract 8 from the x, and keep the y the same. Or the second choice was keep the x the same and change the y. All right, so what did we do? We kept the x the same, and we changed the y. So that's going to be this one. Where would this choice put us, where we subtract 8 from the x and kept the y the same? Well, that would be a slide going this direction. Oop, you didn't see that at all. Psych. All right, let's try that again. If we kept the, what did I say? If we kept the y the same and subtracted 8 from the x, you're going to be moving along the x-axis. So that would slide you, I'm trying to keep my fingers out of the way. That would slide you this way. See how our x-coordinate didn't change, I mean our y-coordinate didn't change, but our x's did? All right, so hopefully you've manipulated enough with these to get those visuals. Don't hesitate to trace these off and move them around your paper, okay? Remember, the coordinate system isn't going to lie to you in terms of stuff like this, all right? All right, good job. Let's do another geometry. Geometry, we love geometry. What did the acorn say when it grew up? Gee, I'm a tree. Get it? Geometry? Come on, that's a good one. All right. All right, let's look at this. A gardener wants to enclose a circular garden with a square fence as shown below. Excuse me. If the circumference of the circular garden is about 48 feet, which of the following is the best estimate for the length of the fencing need? Can you see that at all? Okay. I don't know. Okay. All right. So let's look at this one. First thing is we need to take a second. The circumference of the circular garden is about 48 feet. So the garden itself is 48 feet. So let's get a grip on that. So circumference is equal to 2 pi r. That's our recipe. And we do know something about it. We know that the circumference is 48, so we could say 48 equals 2 pi r. So what could we get out of that? Well, we know what pi is, and we know what 2 is, so we could backtrack a little bit and say 48 divided by pi, which is about, 48 divided by 2 pi, there we go, sorry, which is about 15.28. All right, I'm going to divide both sides by 2 pi. There we go. You see that? Okay. So we know that the radius is about 15.28. So there's our radius right there, about 15.28. Well, what does that have to do with anything? Well, if our radius is 15.28, what happens if you extend this over and create a diameter? Wait a minute, let me double check my math on that. 48, hold on, 48 divided by 2 divided by pi. See, I did do that wrong. Got to use my calculator, don't I? So my radius is about 7.64. Is that better? 7.64. So if my radius is 7.64, if I go all the way across, what is that? That is a diameter. My diameter, you double it, is about 15.28. Okay? Now the other way we could have gotten there, and this is probably where I would have been better off looking forward, but circumference also equals diameter times pi. So in this case, I could have said 48 divided by pi equals the diameter, and that would have gotten me there a lot faster. Okay? Either way works. But you know how I triggered it for myself is when I wrote down the r, I realized that I was going all the way across. You have to be real careful. So don't hesitate to touch these problems and label things. All right, so now we know that the diameter is 15. Well, you know what? The diameter is 15 in all directions, isn't it? Or about 15.28. So I can take this and slide it over. So isn't the length right here of the square around it also a diameter? And the length going this way is also a diameter. Diameter, diameter, the equivalent of the diameter, right? And the question is a gardener wants to enclose the garden if the circumference is, which of the following is the best estimate for the length of the fencing needing? So what are they really asking? They're asking for perimeter. So isn't that the diameter or the value of those outside pieces 4 times? So what is 4 times their diameter is about, let's see, 15.28 times 4 is about 61.12. So if I come back and look at our answers, we have a choice of 31, 61, 122, 244. Hello, 61 is pretty close. Now actually, if he was going to the lumber store, he would have to buy a little bit more, wouldn't he? He wouldn't just buy 61. He might buy 62 feet to deal with that extra piece. But you never know. Hammer it tight enough, maybe you can make it work. All right, good problem. So the key on that one, and I almost made a mistake with that one. The key on that one is you have to be sure that whichever formula you're using, you have to memorize this one. Circumference is 2 pi r. I solved for r, but when I did my arithmetic, I actually put down the diameter, didn't I? I was thinking too fast ahead. So just take your time, write the recipe, look for what you're, take a second to solve for what you're looking for, and make the conversions there right there in the paper. The more you just sit there and type in on your calculator, you're not going to be able to go back and check your work, okay? All right, let's look at another one. Is there another one? Here's another one. Is a good one. All right. Jill wants to measure the width of the river. She marks the distances as shown below in the diagram. All right, let's backtrack just slightly. You go into the test. You get in there. It's 8 o'clock or 8:15 or whatever time your test starts. I don't know. You get in there, and the first thing, they sit you down. They say, be quiet. Not one single word from you, right? Okay, so no, you're not allowed to talk. You're not allowed to look at your neighbor. You have to stay focused on the paper. All right, so there's a lot of anxiety, a lot of anxiety. Then they come around with the calculator, and what do? Flip over. So they go to the calculator, and they go second, memory, reset memory, all memory reset, done. Your memory has been reset, okay? All right, so now you're ready to take the test. Well, geometry and algebra 2, before you start taking the test, Om. You know what I'm doing? I'm putting myself in the right mode for the test. Om, mode. I'm in the right mode for the test. I know you're laughing and thinking, oh my gosh, she's so stupid. But one of the things your teachers cannot tell you is to put your calculator in the right mode. Okay? So I'm about to do a trig problem. I know it's a trig problem because I've already worked this out. But right now, if I asked you, what is the sine of 30 degrees? Raise your hand if you know what that is. All right, some of you do, some of you know, some of you don't know. If you're an AFM, you better have raised your hand, right? Because that's one of those things that are a pre-calculus you have to know, right? You have to memorize some of those. But if you haven't known that you had to memorize it, if we go over to the calculator and I type in the sine of 30 degrees, and here I do my SOHCAHTOA problem and I work it out, does that mean anything to you? Some of you it might mean something just because that negative popped up, but what if I said, what is the tangent of 30 degrees? That another negative popped up. But if you haven't memorized those values, you're not going to know whether that's right or wrong. Okay, so what's going to happen is that they are going to put the answer in there that works with that problem. Now, what is really the sine? Well, let's go back to the calculator. You need to hit the mode button. And see, the very first one says normal, float, and then it says radians versus degrees. Do you even know what a radian is? Again, some algebra 2, but definitely pre-calculus and AFM, you better be raising your hand to know what a radian is. But you haven't learned what a radian is right now. So you know what degrees are. So you have to change, you have to force the mode over to degrees. Change the mode to degrees. If you don't do that, you're going to get the wrong answer. So now if I come back and I say, what is the sine of 30 degrees? Now the sine of 30 degrees is 0.5, which is a half. And that's correct. But you wouldn't have known that if you hadn't have memorized those values. So what are you going to do as soon as you get your calculator? Home mode, proper mode for the test. Because they're going to have both answers, and you're not going to know when you're so busy typing stuff in which one is right, okay? So promise me, put yourself in the right mode for the test. Fix it on your calculator. Okay, back to our regularly scheduled problem. Can you see it? Yes. Okay. Jill wants to measure the width of a river. She marks the distance as shown in the diagram. Using this information, what is the approximate width of the river? Well, I guess she could just throw a ruler across or throw a tape measure across, but that's not real practical. So one of the applications, which is pretty powerful with similar triangles, and you know what, this one might not even be trigonometry, but similar triangles and trigonometry is that you can make relationships and measure something small on one side to get a larger measurement on the other side. So if we take a second and analyze this, see how they went out of their way to make the right angle? Okay, so we know that these lines are what? They are parallel, because two lines that are perpendicular to the same line are parallel to each other. So we have parallel lines, which means we have alternate interior angles. We also have vertical angles, which are congruent. So one of the things we know for sure is that these two triangles are congruent by angle, angle. Okay? Or not congruent, they're similar. So the two triangles are similar by angle, angle. And if triangles are similar, what does it mean to be similar? If triangles are similar, then one of the things you know is that all the angles are congruent. Fine, we got that. But all the corresponding sides are in proportion. So let's take a second and look at that. That means that CD, this side right here, is in proportion to EA over here. And side CB is in proportion to AB. And side D, where'd I go? DB, here we go, is in proportion to EB. So if all those are in proportion, let's see what values we have. For CD, we have 10. And for EA, we don't know. Let's call that X. In fact, what are we trying to find? We're trying to find the width of the river. So that is the value we're looking for right there. I called X. We're looking for EA, so I'll call that X. What else do we know? CB, do we know CB? CB is 8. And AB is 12. And do we know DB? No, we don't know anything about DB, and we don't know anything about EB. But you know what? We don't need to know anything else. Because what have we just done? We have just set up a proportion with one variable. And one of the things you know you can do with this proportion is cross multiply and solve. So 8x equals 120. Divide both sides by 8. We're left with x equals 15. So what is that representing? X is representing the width of the river. So the width of the river is 15. All right? Wonderful. All right, so I thought we were going to do trig because I saw a triangle. Instantly a right triangle, and what did my mind do? Went to trig. But you're still going to put yourself in the right mode for the test. All right, do we have another one? We have a caller. Yay! Ooh. Okay, East Wake. Caller is Jeremy, Algebra 2. Simplify 1 plus 2i over 2 minus 3i. Well, Algebra 1, you might be thinking that I is just a variable, but this is more than just any variable. This is what? An imaginary variable. That's right, an imaginary number. So one of the things we need to remember is how our imaginary numbers fall together. So let's take a second and remind ourselves that if we have I, that is the square root of -1. And if you square I squared, -1, square root of -1 times the square root of -1 is what? -1. And if we cube I, square root of -1 times the square root of -1 times the square root of -1 is what? Well, negative square root of -1, so that's -I. We continue around, I to the 4th. Square root of -1 to the 4th power would be -1 times -1, which is +1. And then it circles back around. And the reason I like to do this is because if for some reason I asked you what is I to the 27th, not that you would sit there and count it, but you could go, this is the 2, 3, 4, 5, 6, 7, 8, 9, all the way around till you get to 27, okay? So the wheel's pretty handy to remember. One of the things that whenever you see problems like this, one of the things you're going to be really working with is probably this I squared. All right, so let's see. How would we approach this? Well, what you need to do is, since I represents a radical, that's why this is not a legal answer. So if they gave you an answer with I, you're not supposed to have square roots in the denominator, correct? All right, so how would we eliminate that I in the denominator? Well, if you multiplied it by the same thing, which is a lot of people, the first instinct is they would multiply it by the same number. If we went and FOILed, we'd get 4, we'd get positive 9i squared, which is fine, but then look at the center terms. You'd have, 2 times -3i, which would be -6i. -3 times 2 would be -6i. That would leave you with -12i. So that wouldn't eliminate the I at all, would it? So one of the things you have to remember is that if you have a family underneath there, you're not multiplying by the same thing, you're going to multiply by the opposite, by the conjugate. When you multiply by conjugates, that's the equivalent of the difference of two perfect squares, and that will eliminate that center variable. All right, so let's do that. So that leaves us with 1 plus 2i times 2 plus 3i over 2 minus 3i times 2 minus 3i. All right, so if we go ahead and do that math, the top, now this might be a case where you might want to use the box. It all depends on how organized you are, but I'm just going to FOIL it out. So 1 times 2, actually just move down. 1 times 2 would be 2. 1 times 3i would be 3i. 2i times 2 would be 4i. 2i times 3i would be 6i squared. All right? And then the bottom one, this is the difference of two perfect squares. So what you can do is you can go ahead and FOIL this out, but one of the things you should remember is it's just going to be the first term, which is 2 times 2, which is 4, minus the square of the last term, which would be 3i squared, which would be 9i squared. I'm sorry, 3i times 3i, which would be 9i squared. Difference of two perfect squares, factors to be conjugates. All right, so we're done, right? No, sillies, we're not done. So what do we do now? We need to put our common terms together. like terms, common terms. 2 plus 7i plus 6i squared over 4 minus 9i squared. Now we're done, right? No, Jeremy, look at the wheel. Look at the wheel. What does I squared represent? I squared equals -1. Our I equals the square root of -1, so we don't have to worry too much about that one, but we do need to simplify that I squared. So let's do that. So 2 plus 7i plus 6 times -1 over 4 minus 9 times -1. And basically what that'll do is just change the sign. So now we have 2 plus 7i minus 6 over 4 plus 9. That we can simplify a little bit better, correct? 2 plus a -6 would be -4, so -4 plus 7i over 4 plus 9 is 13. That is our answer. Okay? Good job. All right, Jeremy. So watch for that. On an EOC, what you might want to look for is the denominator first off, because that's the key right there. You might just want to work out the denominator and see if that answer pops up. All right. Good luck tomorrow, Jeremy. All right, I think we've got time for another one. Getting close. All right. 2. What is the log form of the equation y equals 20 raised to the -2? You can't do it at all. 3/2 power. Well, one of the things you need to do is remember the basic format for logarithms. And that is, and I'm not putting this in very technical terms, I just want to put it so you can remember it. The log of a base given the solution equals the exponent. Exponent. There we go. Which means a solution equals a base to an exponent. So if I label the parts like that, what we can do is you can very easily see that there's a solution. So see in our problem we have y equals 20 to the -3/2 power. So what do we have? We have the solution, we have a base, and we have an exponent. So convert that to logarithmic form. It would be the log of the base, well the base was 20, of the solution, which in this case is y, equals the exponent. Well the exponent was -3/2. Now, this problem didn't ask us to solve this. It simply asked us to put it in logarithmic form. So is that one of our choices? I hope so. Let's see. Sure is. Look at that. Okay? So remember your conversions. All right. Well, I think that's it. Do I have enough time? Before we end, I would like to thank very much the people who have helped with the show. I'd like you to email us and tell us if there's anything we can do better. But I'd like to thank Gary McConaughey, Knightdale Town Manager, and Matt Barnett, who was our cameraman extraordinaire, for helping me and helping you all have a great show. And hopefully we'll see you next fall. So don't forget to email and do great on those tests, okay? All right. Bye-bye.